In this video, I'm going to talk about applications where the divergence theorem can give us information about the flux into or out of a region that involves some kind of vector field. One of the applications that we can use the divergence theorem on involves Gauss's law. Gauss's law is a fundamental law in physics that states that the electric field due to a point charge Q located at the origin that's inside of a region where the electric field is active is given by an inverse square law. An inverse square law is something that is proportional to 1 over something squared. And in this case, it's 1 over the magnitude of the vector r squared. Let's see how that comes out of Gauss's law. Gauss's law has a vector equation that looks like the electric field as a function of x, y, and z is equal to q divided by 4 pi epsilon naught times the vector r over the magnitude of r cubed. And I know I mentioned that an inverse square law is proportional to 1 over the magnitude of r squared. But keep in mind, if I factor that second term, I get the vector r over the magnitude of r. That's just a unit vector in the direction of r. And then I multiply that by 1 over the magnitude of r squared. That's the term that gives me the inverse square field that we're talking about. And keep in mind, my vector r is a vector with components x, y, and z, and epsilon naught is a physical constant called the permittivity of free space. Now, as you look at this vector equation, notice that q over 4 pi epsilon naught, that is comprised of only constants. None of those terms are variables. So there's my proportionality constant right there. That's one constant. And then my unit vector, r over the magnitude of r, is the vector in the middle. And then times 1 over r squared gives me the inverse square term. The divergence of this field will be something that is computed using the second term, the vector r divided by the magnitude of r cubed only, and then multiplying by that constant that's out front. So now I want to look at the divergence of an inverse square field that doesn't have all those leading coefficients in front of it, so that we can see exactly what the result is when we do that. I'm going to let my f vector be equal to the vector r divided by the magnitude of r cubed. This can be written as the vector with components x, y, z over the quantity x squared plus y squared plus z squared to the 3/2 power. That is the magnitude of r cubed. Now I want the del dot f, which gives me the divergence of this field. So del dot f is the dot product of a vector with components the partial with respect to x, the partial with respect to y, and the partial with respect to z, which means I take the partial of that quotient with respect to x, and then I add the partial of the quotient with respect to y, and then I add the partial of the quotient with respect to z. I do all of those partial derivatives using the quotient rule. When I get that done, I end up with 3 terms on my del dot f. It's equal to the quantity of x squared plus y squared plus z squared to the 3/2 times 1 minus 3x squared times the quantity x squared plus y squared plus z squared to the 1/2 power over the quantity x squared plus y squared plus z squared cubed. And I add to that the quantity x squared plus y squared plus z squared to the 3/2 power times 1 minus 3y squared times the quantity x squared plus y squared plus z squared to the 1/2 power all over the quantity x squared plus y squared plus z squared cubed. And then I add a third term, the quantity x squared plus y squared plus z squared to the 3/2 power times 1 minus 3z squared times the quantity x squared plus y squared plus z squared to the 1/2 power all over the quantity x squared plus y squared plus z squared cubed. Now I'm going to use some algebra. I'm going to factor a common term of the quantity x squared plus y squared plus z squared raised to the 1/2 power out of the numerator. This gives me the quantity x squared plus y squared plus z squared to the 1/2 power over x squared plus y squared plus z squared cubed times the quantity x squared plus y squared plus z squared times the quantity negative 2x squared plus y squared plus z squared plus x squared minus 2y squared plus z squared plus x squared plus y squared minus 2z squared. Watch your signs, and now we combine like terms. When we combine like terms, everything in this particular part of my equation sums to 0. So I end up with a 0 divided by the quantity x squared plus y squared plus z squared to the 5/2 power is equal to 0. This is a radial field, and in a radial field the divergence is 0. So now that we have the divergence for this inverse square field, let's find what the flux is. That's the flux into or out of. And we know from our divergence theorem that the volume integral of del dot F is equal to the surface integral of f dot n sub 2 ds minus f dot n sub 1 ds. And that difference of those two surface integrals is 0. So that we can use either of these surface integrals here to compute what my net inward or outward flux is. Keep in mind that I've got an outward flux of S sub 2 and an inward flux of S sub 1. I can use either of those surface integrals because their difference is 0. And so I'm going to use F is equal to R over the magnitude of R cubed, with N sub 1 being equal to R over the magnitude of R, which is the unit normal vector that we talked about. And that tells me that my surface integral over S sub 1 is F dotted with N sub 1 ds, which is equal to the surface integral over S sub 1 of R over the magnitude of R cubed times the unit normal vector R over the magnitude of R ds. When I multiply those through, I get the surface integral over S sub 1 of the magnitude of R squared over the magnitude of R to the 4th ds, but my R is going to be the radius of my region. And because it's spherical, I'm going to just let R be equal to A. It's just going to be a constant for this field. So that's going to give me a surface integral of 1 over A squared ds, where 1 over A squared is a constant for the field I'm working with. I can factor that 1 over A squared out front, and it's just a surface integral. The surface of a sphere is 4 pi times the radius squared, which is 4 pi A squared in this case, because that's the radius of my sphere. And I divide by A squared so that my flux for this inverse square field is 4 pi. And this is true for any inverse square field, because you'll notice the radius of A is going to cancel out no matter what it is. So when I have an inverse square field, my flux is going to be 4 pi. So now let's take that piece of information and look again at Gauss's law. You'll notice that my electric field is equal to that big constant out front times r over the magnitude of r cubed. Since this is a constant times an inverse square field, the flux is going to be given by my constant q over 4 pi epsilon naught times the flux for the inverse square field, 4 pi. 4 pi cancels out, and I get my flux for this electric field, which is an inverse square field, is q over epsilon naught. And you'll notice that it doesn't matter what the electric field looks like. I don't have to know. I know that that flux is going to be q over epsilon naught. So now let's work an example that is similar but not identical to what we just did. The gravitational force due to a point mass m at the origin is proportional to F, which is equal to g times m times r over the magnitude of r cubed. This looks very similar to what we saw before when r is a vector with components x, y, z, and capital G is the gravitational constant and capital M is the mass of the point. Find the flux of the force field across a sphere of radius a. Now we're not working with Gauss's law, but we're working with something that looks extremely similar. It's an inverse square field, and I know that the flux across the surface is going to be given by 4 pi times the constant in front of the r over magnitude of r cubed term. In other words, my flux across the surface is going to be 4 pi times g times m. And we're done. It's just that easy. Here's another application. This one's again a little different. It's not an inverse square field. In this case, I have a direct proportionality. This is Fourier's law of heat transfer, which states that heat energy always flows from hot to cold regions. And it's written as the heat flow is proportional to the negative gradient of the temperature. The negative sign is telling me it's going from hot to cold. So my force F is equal to negative K times delta T, and K is the conductivity constant. And when I have this kind of heat transfer problem, I can then note that the net outward heat flux across the surface of a region D will be given by the surface integral of F dot n ds will be equal to negative K times the surface integral over S of del T dot n ds. So let's work an example. I want to find the net outward heat flux for a thermal field that's equal to negative K del T, assuming K is 1. My thermal equation, T of xyz, is equal to 100 plus x plus 2y plus 2z, and my region D is the set of all xyz such that 0 is less than or equal to x, which is less than or equal to 1, 0 is less than or equal to y, which is less than or equal to 1, and 0 is less than or equal to z, which is less than or equal to 1. I'm going to write out the divergence theorem with the volume integral of del dot f dv set equal to the surface integral of f dot n ds, which is equal to negative k times the surface integral of del t dot n ds. F is equal to minus k del t. When I do del times my t equation, I get a vector with components negative 1, negative 2, and negative 2. That's using 1 for k and distributing that negative into my vector equation for f. Del dot f is a dot product between the del vector and my f vector, and I get 0 for that because my f vector is all constants and the partial derivatives of constants are all 0. So now I know that my divergence is 0, And that tells me that negative k times the surface integral of del t dot n ds is equal to 0 as well. So now you get to try it. Pause the video and find the net outward heat flux for F is equal to negative del T when T of xyz is equal to 100 plus x squared plus y squared plus z squared, and D is a unit sphere centered at the origin. Assume K is 1. When you are ready, restart the video to check your understanding. What I want to do is write out my divergence theorem. My volume integral over d of del dot f dv is equal to the surface integral over s of f dot n ds, and I set that equal to negative k times the surface integral over s of del t dotted with n ds. My f vector is negative del t because I'm assuming k is 1, and that gives me a vector with components negative 2x, negative 2y, negative 2z. This tells me that if I factor out a negative 2 and bring it out in front of my surface integral, I get negative 2 times the surface integral of del t dot n ds. Keep in mind I'm going to plug in my dot products here. So I'll plug in my del t vector and my unit normal vector. This is going to give me negative 2 times the surface integral of the vector with components x, y, z dotted with the vector with components x, y, z divided by 1. That's because x squared plus y squared plus z squared is equal to 1 because that's a unit sphere. And then I take that integration with respect to ds. This gives me negative 2 times the surface integral over s of 1 ds. The surface of a unit sphere has the value 4 pi, so I get negative 2 times 4 pi is equal to negative 8 pi. That is the net outward flux for F is equal to minus k delta t. Let me know if you still have questions.